Hello friends, today we will discuss about the important ingredient in concrete, that is aggregate. There are four ingredients in concrete: cement, water and coarse aggregate and fine aggregate. Out of this, the aggregate are about 80 to 85% of the volume of concrete. Coarse aggregate are 50%, whereas fine aggregate are of 31%. So total aggregate volume is 80 to 85%. The importance of coarse aggregate, the role of coarse aggregate is the role of bone in our body. It is just like role of our bone in our body. It the coarse aggregate gives strength, stiffness to the concrete, whereas fine aggregate fills the voids of the coarse aggregate and make the concrete dense. Fine aggregate also reduces shrinkage and increases impermeability of concrete. So this is the importance of coarse aggregate and fine aggregate. Now let us see what are the different types of aggregate. The classification of aggregate. Aggregates are classified according to the origin: natural, that is sand and gravel; artificial, that means broken bricks. According to the size, aggregates are classified as fine aggregate, having size less than 4.75 mm, that is passing through 4.75 mm sieve and retained on 75 micron sieve, whereas coarse aggregate are the aggregate having size greater than 4.75 mm. According to the shape, the aggregates are classified as rounded, that is fully worn; irregular, rounded, irregular, then angular, then flaky and elongated. Out of this, the rounded aggregate are very good for workability, but due to poor interlocking, they give less compressive strength. The flaky and elongated aggregate are poor in workability as well as they are very poor in compressive strength of concrete. So always prefer angular aggregate. Angular aggregates are preferred for making concrete. Then according to the unit weight of aggregate, normal weight, that is specific gravity, between 2.5 to 2.7. Heavyweight aggregate, specific gravity between 4 to 5.3, and lightweight aggregate, the specific gravity between 1.5 to 1.8. Then according to the surface texture, the aggregate may be smooth textured or rough textured. Smooth textured aggregate gives better workability, but rough texture aggregate give greater compressive strength. What are the characteristics of aggregate? We will see one by one: particle size, particle shape, surface texture, specific gravity, bulk density, water absorption, bulking of sand, soundness, surface moisture, deleterious materials, strength of aggregate, and alkali aggregate reaction. We will see each characteristic in brief in further slides. Particle size. The size of aggregate can be determined by mean of sieve size. It may be from 80 mm to 75 micron. Aggregates are used according to their size in different construction works. For dams where mass concreting is done, 40 size is used. For normal building RCC beams and for RCC beams and columns, 20 size of aggregate is used, whereas for floor construction, slab construction, 10 size aggregate is used. Then let us see what is the shape of aggregate. Shape of aggregate depends upon the source of aggregate. The shape may be rounded, irregular, angular, flaky, and elongated. The shape of aggregate affects the workability of concrete, its strength, and of course its durability. Shape of aggregate affects compressive strength by 22% and flexural strength, that is bending compression strength, 30%. Then flaky aggregate. The apparatus shown in the photograph is used to check whether the aggregate is flaky or not. From a particular size slot, the aggregate is passed, and if it is passed, then the aggregate can be termed as flaky aggregate. Now, to which aggregate we can call it as flaky? The aggregate is said to be flaky when its least dimension is less than 3/5 of its mean dimension. Mean dimension is the average size through which the particles pass and the sieve size on which these are retained. The flakiness index of aggregate is the percentage by weight of particles whose least dimension, that is thickness, is less than 3/5 of their mean dimension. These flaky aggregates poor are very poor in making concrete as they have got very poor workability. Then elongated aggregate. Elongated aggregate, the particle is said to be elongated when its greatest dimension, that is length, is greater than 9/5 of its mean dimension. The apparatus shown in the figure is used to check whether the aggregate is elongated or not. From the particular slot, the mentioned size of aggregate is passed. If it is passed, then it is not elongated, but if it doesn't pass, then it is termed as elongated aggregate. Elongation index is the percentage by weight of particles in it whose largest dimension, that is length, is greater than 9/5 of its mean dimension. This aggregate, elongated aggregates, is also not preferred for making concrete. Surface texture of aggregate. The surface of the aggregate may be smooth or rough. The surface of the aggregate depends upon the hardness, size, and pore characteristics of the parent rock. Aggregate with smooth surface develop a poor bond than rough surface. But rough texture aggregate reduces workability but gives good compressive strength. Specific gravity of aggregate. Specific gravity of aggregate is the indicative of its quality. A low specific gravity indicates high porosity and therefore result in poor durability and low strength. The specific gravity of most aggregate varies from 2.4 to 2.9. Apparent specific gravity. It is the ratio of weight of aggregate to the weight of water occupying the volume equal to that of solids of aggregate, excluding pores in the aggregate. Whereas bulk specific gravity, it is the ratio of weight of aggregate to the weight of water occupying the volume equal to that of solids of aggregate, including pores in the aggregate. Bulk density of aggregate. The weight of aggregate that would fill a container of unit volume is known as bulk density. Factors affecting bulk density are grading of aggregate and shape of aggregate. See, bulk density is its weight per unit volume. The bulk density is measured in kilonewton per meter cube. Loose bulk density. It is determined by filling the container without any compaction. It is loosely filled in the container. Whereas compacted bulk density, also known as rodded bulk density, is determined by filling the container in three layers and each layer is compacted with 16 diameter rod. Definitely, compacted bulk density is always greater than loose bulk density. Water absorption of aggregate. All aggregate particles have pore within its body due to which it absorbs water. Water absorption shall not be more than 0.6% by weight. Aggregate absorption is the increase in mass due to water in the pores of the material. Aggregate absorption is a useful quality because high value can indicate non-durable aggregate. Bulking of sand. The volume of dry sand increases due to presence of moisture in it. This volume increase of dry sand is known as bulking of sand. When dry sand comes in contact with moisture, a thin film is formed around each particle of sand, and due to the property of surface tension of water, the film pushes the surrounding sand particles apart by giving increase in volume. The amount of bulking depends upon particle, size of sand particle and amount of moisture in it. This property is very important when we are batching the concrete by volume batching, because if the sand is moist, the actual volume of sand may be less than the measured volume of the sand. This graph shows the effect of moisture on percentage increase in volume. Now there are three curves. First, fine sand. Here we get more bulking than medium sand or coarse sand. So bulking depends upon the size of sand, and as the percentage of moisture increases, we get increase in the volume up to certain limit, and after that the volume again goes on reducing. Surface moisture. Natural aggregates generally contain moisture. The moisture on the surface determines the free water in to be considered while measuring the water cement ratio, because the free water present in on the surface of the aggregate will add and water cement ratio may rise. So accordingly we will have to adjust water cement ratio. Deleterious materials in the aggregate. Deleterious materials in the aggregate are those substances which detrimentally affect the fresh and hardened properties of concrete. For instance, strength, durability, and long-term performance of the concrete in which such are used. Deleterious materials are highly undesirable constituents. They are divided into following groups: organic impurities, silt and clay, and unsound or weak particles. Organic impurities may be of animal waste, leaves of the trees, silt and clay, and unsound or weak particles means shells. Strength of aggregate. The resistance of aggregate to compressive load is its crushing strength. Usually, aggregate is considered to be 10 times stronger than the crushing strength of concrete. Aggregate to be used in concrete should not be weaker than the strength of hardened cement paste. Otherwise, what will happen? The joint between the two aggregate due to the cement paste, hardened cement paste, will remain intact and aggregate will break. This should not happen. The strength of aggregate should be more than the strength of hardened cement paste. Alkali aggregate reactions. Alkali aggregate reaction is a term mainly referring to a reaction which occurs over time in concrete between the highly alkaline cement paste and non-crystalline silicon dioxide, which is found in many common aggregates. The reactivity of aggregate is affected by particle size and its porosity, quality of cement, permeability of paste, and availability of water in paste. So these are the factors which affect alkali aggregate reaction. Grading of aggregate. Grading refers to the determination of the particle size distribution for aggregate. Grading limits and maximum aggregate size are specified because these properties affect the amount of aggregate used as well as cement and water requirements, workability, pumpability, and durability of concrete. Now, these are the different types of grading. In this first picture, you will see single sized aggregate. It is also known as uniformly graded. All the sizes are of same size, so it is uniform, so uniformly graded. Then this is poorly graded. It is also known as gap graded. Here you can see that only two size aggregates are available. In between size of aggregate is absent, so it is also known as gap graded. Both uniformly graded and gap graded are poorly graded. As you can see, volume is more in both the cases, whereas the well aggregate in which all the size of aggregates are present, so voids are minimum. As voids are minimum, the cement paste required to fill up that voids is less. So more cement paste is available as a lubricant. So well graded aggregate gives good workability as well as voids are less. So it is a dense and strong concrete. So always prefer well graded aggregate. In this slide, the description of these three types of grading is mentioned. Well graded aggregate, it means all the size of aggregates are present, voids are less, therefore gives dense concrete. It is preferred for making concrete. Whereas poorly graded aggregate, it contains aggregate particles that are almost of the same size. This means that particles packed together leaving relatively large voids in concrete. It is also called as uniformly graded aggregate. And the gap graded aggregate means intermediate size is totally absent. In this also voids are more. Poorly graded aggregate and gap graded aggregate are not preferred for making concrete. Then let us see what is fineness modulus. The fineness modulus FM is an empirical figure obtained by adding the total percentage of the sample of an aggregate retained on each of specified series of sieves and dividing the sum by 100. A smaller value of fineness modulus indicate a finer aggregate and larger fineness modulus value indicates that the aggregate is coarser. This is the formula which determines the fineness modulus of the given aggregate sample. Fineness modulus is equal to the cumulative percentage retained on each sieve divided by 100. How the fineness modulus is calculated in laboratory? If it is a fine aggregate, the sieves are arranged like this. At the top 4.75, then 2.36, 1.18, 600 micron, 300 micron, 150 micron and 75 micron and then pan. Suppose 1 kg of sample is taken of fine aggregate, then it is kept in top sieve, that is 4.75 mm, and it is sieved for say 15 minutes. Then the mass of sample retained on each sieve is measured and it is noted down in the table. Suppose on 4.75 mm sieve, the mass retained is 10 gram. On 2.36 mm sieve, it is 50 gram. On 1.18 mm sieve, it is 100 gram. 600 micron on this, the mass retained is 320 gram. 300 micron, the mass retained is 460, and on 150 micron, 50, and remaining is on 75 micron and in the pad. Then percentage mass retained is calculated. We know that the total mass is 1 kg, that is 1000 gram. So 10 divided by, I can write here 10 divided by 1000 into 100 for percentage. So we get 1% here. Similarly, 50 divided by 1000 into 100, we get 5 here. 100 divided by 1000 into 100, that is 10. So likewise, the percentage of mass retained on each sieve is calculated. Up to 150 micron, it is considered. Then cumulative percentage mass retained is calculated. That is, mass retained on 4.75 mm is percentage is 1. 1 plus 5, 6 here. 6 plus 10, 16. 16, 1 plus 5, 6. 6 plus 10, 16. 16 plus 32, 48. 48 plus 46, 94. And 94 plus 5 is 99. Then the sum of all the masses, cumulative percentage mass retained is taken. In this case, it is 264, and the fineness modulus is calculated by the formula 264 divided by 100, that is 2.64. This is a simple practical which determines the fineness modulus of the given sample. The sand is said to be fine when the fineness modulus is between 2.2 to 2.6. Medium sand, the fineness modulus is 2.6 to 2.9. Coarse sand, the fineness modulus is between 2.9 to 3.2. Now, when we want to calculate fineness modulus for coarse aggregate, the sieve size are from 80 mm, then 40 mm, 20 mm, 10 mm, 4.75 mm, 2.36 mm, 1.18 mm, 600 micron, 300 micron, and 150 micron. Here I have given purposely the serial number in the reverse order. The bottommost sieve I have mentioned 1, then 2, 3, 4, 5 up to 10. 80 mm sieve I have numbered it as 10. Then suppose the mass of 10 kg of coarse aggregate is taken. It is sieved from the sieves which are arranged from top to bottom as 80 mm to 150 micron. Then mass retained on each sieve is measured. Percentage is calculated like in the previous case. Then cumulative percentage is calculated. Then add all the cumulative percentage retained. In this case it is 683. Now fineness modulus is 683 divided by 100, that is 6.83. What does it indicate? 6.83. It means most of the sample belongs to sieve size between 7 and 8. As it is 6.83, the sieve number between 6 and 7 measured from bottom. So this is 1, 2, 3, 4, 5, 6 and 7. So majority of sample you can see that means out of 10 kg 2.6 and 3.6, that is 6.6 kg belongs to sieve number 6 and 7 measured from bottom. So this is the meaning. In the previous case also, the fineness modulus was 2.64. It means majority of the sample belongs to sieve number 2 and 3. Sieve number 2 and 3 measured from bottom. Remember, it is measured from bottom. So the majority of the sample belongs to size 300 micron and 600 micron in the in this problem, and in the coarse aggregate problem majority of the sample belongs to size 4.75 mm and 10 mm. So this is the information we get from fineness modulus. Now the questions which are often asked in concrete technology subject in theory examination: what is the role of aggregates in concrete? Classify aggregates according to size, shape, surface texture, and unit weight. Define flaky and elongated aggregates. What are the deleterious substances in the aggregate? What is grading of aggregates? Define well graded, poorly graded, and gap graded aggregate. Why well graded aggregates are preferred for concreting? What is bulking of sand? On which factors bulking of sand depends? What is bulk density of aggregate? On which factors bulk density of aggregate depends? What is fineness modulus? A numerical example can also be asked like this. You will be given the total mass of the sample and the mass of sample retained on each size sieve will be given. Now in that case you will prepare a table just that I explained earlier. Find the percentage mass retained on each sieve. Then find the cumulative percentage retained in each sieve. Add the total of cumulative percentage retained up to 150 micron and divide that sum by 100. You will get fineness modulus. So this complete our small chapter of aggregate. Thank you very much.